Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and today in the top 30 MCQ series we are going to discuss electromagnetic induction. This is also a medium important chapter. 3 questions usually coming from this chapter every year. So we are, without any delay, we will check all the questions from this chapter. Let's start with the first question. The current in a coil changes from 2 ampere to 5 ampere in 3 seconds. The magnitude of the EMF induced in the coil is 1 volt. The value of the self-inductance of the coil is. So current in the coil changes from 2 to 5 ampere. So current changes means DI. So DI is 5 minus 2, that is 3. Change in the current is DI, the time is dt, which is equals to 0.3 seconds, okay, and induced EMF is 1 volt. So induced EMF is 1 volt. You have to find the self-inductance of the coil. We know that induced EMF is L di by dt. Okay, so induced EMF is 1 volt, L is we don't know, di is 3 and dt is 0.3. So L equals to 1 into 0.3 divided by 3. Okay, cross multiplication, simple. So you will get, it will be 0.1 Henry. 0.1 Henry. Now if you check the options, not a single option is given 0.1 Henry. Be careful, this is millihenry, not Henry. So what you have to do, you have to consider it to be 100 millihenry. What is millihenry means? Milli means 10 to the power of minus 3. So the answer will be 100 millihenry. So be careful, don't just randomly mark this as correct. This is why KCET is slightly trickier. Even though the answer is easy, question is easy, solvable, but options sometimes are little tricky. Now next question. A metallic rod of length 1 meter held along east-west direction is allowed to fall down freely. Okay, so there is a metallic rod held along east-west direction. It is allowed to fall down freely given the horizontal component. Of Earth's magnetic field is basically 3 into 10 to the power of minus 5 Tesla. So BH is 3 into 10 to the power of minus 5 Tesla. Okay, length of the rod is 1 meter. Okay, it is allowed to fall freely means it is falling under the action of gravitational acceleration. Okay, the EMF induced in the rod at an instant 2 seconds after it released. So you have to find the induced EMF after 2 seconds. So what is the formula? Induced EMF is BVL. Now V is not given here, B is given, L is 1 meter. What about V? So we will use our knowledge in the from the first few chapters, that is falling under gravity freely. So what will be its velocity? Velocity will be acceleration into time. It is starting from the rest, so U is 0. So basically formula is V is equal to U plus AT. Now U is 0, A is equals to G. So simple formula is this. So 10 into time is given 2 seconds. So speed will be 220 meter per second. Now use the formula. B is 3 into 10 to the power of minus 5. V is 20. L is 1 meter. So it will be 60 into 10 to the power of minus 5, or it will be 6 into 10 to the power of minus 4 volt. Okay, so answer is 6 into 10 to the power of minus 4 volts. Next question. The following figure shows a conducting rod moving towards left. So here we have a conducting rod moving towards left with a velocity v. Okay, the whole setup is placed in a perpendicular magnetic field, obviously which is into the page of the paper. Okay, now we have to find whatever the statement is correct. The direction of induced current in the left part is anti-clockwise and in the right part is clockwise direction of, okay. So we are basically trying to find the direction of current in each of the parts. So what formula we will use? We can either use the cross product rule, or we can use the Fleming's right hand rule. I am teaching you Fleming's right hand rule. Always remember that this finger represents the direction of magnetic field and your thumb represents the direction of motion, and then your middle finger represents the direction of current. So we will first point our index finger towards the magnetic field. So magnetic field is into the page of the paper, so here this finger goes towards the page of the paper, and then we will point our thumb towards the motion. So motion is in this direction, and then this finger, the middle finger, will point the direction of current, which is downward. So current is passing through the rod in the downward direction. So downward direction means what? Now how can the current be downward? Through this loop. Through this loop it can be downward only if the current is flowing like this. Okay, so current will be clockwise. So this is a clockwise direction. Clock rotates in this direction, so this is clockwise. And through this loop it can be downward only if it is going in the anti-clockwise direction. Okay, now both will have induced current in it because area is changing in both of them, but the direction of current through the rod for both cases will be the same. Direction of the rod, current in the rod will be same, but current through this loop will be anti-clockwise, whereas this one will be clockwise. So on our left hand side it is clockwise, on our right hand side it is anti-clockwise. So direction of induced current in the left part is clockwise and on the right part it is anti-clockwise. So correct answer is option B. Next question. A long solenoid has 500 turns. When a current of 2 ampere is passed through it, the resulting magnetic flask linked with each turn of the solenoid is 4 into 10 to the power of minus 3 Weber. Then the self-inductance of the solenoid is. So again we have to find the self-inductance. Okay, magnetic flask linked with the each turn of the solenoid is this. So what is the total magnetic flask? Total magnetic flask is basically N into magnetic flask through one single coil, which is total is 500 turns, and from one of the turn is 4 into 10 to the power of 3. You can consider this to be d phi as well. Okay, the change in the flask, because this is linked means this is changing as well. So it will be 4 into 5, 2000 into 10 to the power of minus 3, that is 2. So d phi is 2. Now so what is the induced EMF? Induced EMF can be calculated using two formulas, d phi by dt, also L di by dt. Okay, so these are the two formulas. Now dt will cancel, so we get d phi equals to L di or L equals to d phi by di. Okay, what is d phi? D phi we have calculated 2. What is current? Current associated is 2 ampere, so current is also 2. Okay, so they will cancel, we get the self-inductance is 1 Henry, right? So correct answer is option C in this case. Next question. A magnetic field of flux density 1 Weber per meter acts normal to a 80 turn coil of 0.01 meter square area. So flux density is given. Flux density means magnetic flux per unit area, that is flux density, and number of turn is given, the area is also given. Okay, if this coil is removed from the field in 0.2 seconds, then EMF induced in it. Obviously EMF induced is d phi by dt. Right, dt is given 0.2 seconds. We have to find d phi. What is d phi? D phi is number of turns, okay, into flux density into the area. This is the flask linked with the coil. So what is number of turns? Number of turns is obviously 80 turns. Total number of turns, remember total number of turns. Flux density is 1 Weber per meter square, and area is 0.01 meter square. So this is the flux density, so it is basically 0.8. Okay, 0.8 is d phi. Now we have to put the value over here. So 0.8 divided by 0.2, so it will be 4 volt. Simple, 4 volt is correct answer in this question. Next question, obviously if you want to practice more such questions and in holistic manner, so that all chapters, all questions are coming, and you want to practice within a given time limit of 60 questions in 60 minutes, then definitely you want to have our Abhyas KCET test series, which is currently available at a price of 1498. The link for this is given in the description, which is very essential for your KCET 2025 preparation. Okay, a lot of students have already registered for you, and register for it. If you have not yet registered for it, go to the link below and register it, for it today. Right now, next, this question: the current flowing through an inductance coil of self-inductance 6 millihenry at different time instances is as shown. The EMF induced between t equals to 20 second and t equals to 40 second. So as you can see, at t equals to 20 second, the current was 4 ampere. It is ampere. So current was 4 ampere at t equals to 20 second, and at t is equal to 40 second, it is 3 ampere. Okay, this exactly between 2 and 4, so it is 3 ampere. So what is the change in current? Change in current is 4 minus 3, that is 1 ampere. What is the change in time? Change in time is final minus initial, that is 20 second. Okay, so what is the self-inductance? Self-inductance is 6 millihenry. So what is the induced current? So induced current will induced EMF will be L di by dt. 6 millihenry means 6 into 10 to the power of minus 3. Di is 1 and this is 20. Okay, so it will be 10, it will be 3, so it will be 3 into 10 to the power of minus 4 volt. So the induced EMF is 3 into 10 to the power of minus 4 volt. Okay, next question. A rod of length 2 meter slides with the speed of 5 meter per second on a rectangular conducting frame. So this rod is sliding along the rectangular conducting frame as shown in the figure. There exists a uniform magnetic field of 0.04 Tesla. Okay, so the magnetic field is 0.04 Tesla perpendicular to the plane of the figure. If the resistance of the rod is 3 ohm, the current through the rod is. So definitely resistance is given. First we have to find the induced EMF. Induced EMF is B V into L. B is given 0.04 Tesla. Velocity is given 5 meter per second, and the length of the rod is given 2 meters. Length of the rod 2 meters, speed is 5 meter per second. So just try to calculate it. So induced EMF is 5 to the 10, 10 into 0.04 is 0.4 volt is the induced EMF. So what is the current? Current will be induced EMF by resistance, that is 0.4 divided by 3, that is 0.75 ampere. So induced EMF is 0.75 ampere. So correct answer is option A. Now let's move on to the next question. The current in a coil of inductance 0.2 Henry changes from 5 ampere to 2 ampere in 0.5 second. The magnitude of the average induced EMF. So as you can see, there are a lot of questions are coming from this average induced EMF. We can expect at least one question from this concept only. So practice BVL related concept, then this motional EMF, that is BVL is motional EMF. Then we have this either of the induced EMF question, epsilon is equal to d phi dt, or directly inductor related questions where self inductance is given. So L di by dt, right? L is 0.2, okay, 5 ampere to 2 ampere, that means di is 3 and 0.5 seconds. I am not wasting any time, so it will be 6 by 5. 6 by 5 means 1.2. So 1.2 volt is the answer. Next question, consider the situation given in the figure. The wire AB is slide on the fixed rails with a constant velocity. If the wire AB is represented by a semicircular wire, the magnitude of the induced current will be. So as you can see, this is a very common diagram. Now instead of this rod, if the wire is semicircular, okay, either this way or this way, okay, then what will happen to the induced EMF? So induced EMF, what is the formula for induced EMF? We know that induced EMF is BV into L. Now if the speed V remains same, magnetic field is constant. If L is same, okay, if the same rod is curved into a rail, as long as length is not changing, the magnetic flask will remain same, okay. So magnetic flask will remain same, it will not change. Next question, a jet plane having wingspan of 25 meter is traveling horizontally towards east with a speed of 3600 km per hour. Given the vertical component of Earth's magnetic field BV equals to 2 into 10 to the power of minus 4 Tesla, then the potential difference between the ends of the wing. Again, same formula, epsilon equals to BVL. Only this case it will be vertical because the plane is moving like this. Okay, plane is moving like this, so only vertical component of magnetic field will be required over here. So BV is 2 into 10 to the power of minus 4. Velocity is, now velocity is 3600 km per hour. 3600 km per hour means it will be 5 by 18 meter per second. Okay, remember this conversion factor, it will be very, very handy. It will be 200 into 5 is 1000 meter per second. Put the value over here, 1000 into L is 25, right? Now 1000 10 to the power of minus 4 will give you 10 to the power of minus 1. So 25 into 2 is 50 into 10 to the power of minus 1, that is 5 volt. So you get a 5 volt battery when you are sitting on a plane, right? Next question. The magnetic flux linked with the coil varies as phi is equal to 3t square plus 4t plus 9. The magnitude of the EMF induced at t is equal to 2. Very easy. Phi is given, 3t square plus 4t plus 9. What is induced EMF? Induced EMF is d phi by dt or d phi dt. dt of phi, whatever you say. 6t plus 4. Okay. So differentiate it, right? So 6 into 2 plus 4, that is 12 plus 4, that is 16 volt. Okay, so 16 volt is the induced EMF. Next question. A bar magnet is allowed to fall vertically through a copper coil placed horizontal plane. The magnet falls with the net acceleration equals to z, equals to 0, less than g, greater than g. So if you allow this magnet to fall through this circular coil freely when the magnet north pole is facing the coil, right? So what will happen? The induced EMF initially it will be such that it will always oppose the motion. So initially when it is falling up to this point, okay, the induced current will be such that the induced EMF it will induce a north pole on this side. So basically the current will be in this direction, and this north pole and this north pole will be repelling each other. But when the coil has already fallen, when the coil is already fallen and the south pole is moving away, then the induced current on the other surface will be south pole, basically same current will be on the same side, okay, and this will try to current direction will reverse. The opposite side will be north pole. Why so? Because the upper side will be south pole. Okay, so that this north and south they attract each other. Okay, so basically current will be in this direction now. So now when the magnet has fallen through the loop, still this north pole will try to stop that south pole and it will attract it. So basically that means that the acceleration of the gravity acceleration of the magnet will be less than that of the acceleration due to gravity. So it will slow down when the magnet is falling through a conducting loop. The magnet will slow down. You can try and test it with a very nice experiment. You can take a copper tube and you can allow a magnet to fall through it. Okay, because of the induced current in the opposite direction, the magnet will fall very slowly. Next question. The working of a magnetic braking of trains is based on, so magnetic braking is based on eddy currents. Okay, it is the same principle. It is basically the induced current. Okay, when you are trying to move through a medium, okay, having magnetic, if you have magnetic field and if you are trying to move through a conducting wire, then that produces a induced current. That induced current actually opposes the cause of it, and because of that it basically stops the train, and this is called eddy current. A solenoid of inductance 1 Henry carries a current of 2 ampere. The magnetic energy stored in the solenoid is, so the magnetic energy stored in the solenoid is given by half Li square. So magnetic energy stored is half Li square. So half or yes, inductance is given half 1 Henry. Current is 2 square. So it will be half into 4. That will be 2 joules. It will, unit is wrong. Unit will be joules. Okay, unit will be joules. Okay, so it will be 2 joules of energy stored in the system. Next question. A long solenoid with 40 turns per centimeter carries a current 1 ampere. The magnetic energy stored per unit volume is, so magnetic energy stored per unit volume is given by half, we do not know the mutual inductance, so there is a formula which says that it is basically B square by mu naught. Okay, it is B square by mu naught. You have to remember this formula. This is very important formula. Okay, so magnetic energy per unit volume is B square by mu naught. Now what is B square, by the way? For a long solenoid, B square is mu naught N into I. N is number of turns per unit length. Okay, and here the unit length should be in meters, by the way. Whole square divided by mu naught. So it is half. One of the mu naught will cancel. It will be mu naught N square I square. This is the formula. Okay. Now here 40 turns per centimeter is given. 40 turns per centimeter. So how can I convert it into meters? To convert it into meters, I have to use 10 to the power of minus 2 meters, or it will become 4000 turns per meter. 4000 turns per meter. Per meter means it is in division. So be careful when you are using the term per, it will be in the division, and accordingly you have to adjust the unit. So it will be 4000 turns per meter. As now we have to put the values. What is mu naught? Mu naught is 4 pi into 10 to the power of minus 7. N square is 4000 whole square. I square is 1 ampere, so 1 square. Now we have to simplify this. So you can cancel this. It will be 2 pi. So 2 pi into 10 to the power of minus 7 into 4 square is 16. And here we have 10 to the 3 zeros. 3 zeros means 10 to the power of 3, and then we have whole square of that, so it will be 10 to the power of 3 whole square. It will be 10 to the power of 6. Okay, so it will be 32 pi into 10 to the power of minus 1. So it will be 3.2 pi. Okay, so 3.2 pi is the answer. Okay, next question. A wheel with n number of spokes, each of length L meter, is rotated with a uniform angular velocity omega in a plane normal to the magnetic field B. The EMF induced between the axle and the rim of the wheel. So here we have a wheel. Okay, basically it is rotating with the angular speed omega. Okay, and the length of the spoke is L, and there are capital N number of spokes. Now if you see that induced EMF is basically, you can say that all the spokes are, there is no resistance of the spokes, so basically you can consider them to be total EMF, okay, induced EMF. Okay, EMF means what? EMF means battery. So all of them are equal induced EMF, and all of them are connected in parallel over here. So they are all connected in parallel because of this rim. Okay, this is the rim part. Okay, so they are all connected in parallel, and because of that you don't need to consider the total number of rod connected. Okay, it can be 100, it can be 1000, it can be 1, it can be 10, does not matter. Number of spoke does not matter in this problem. This is a very specific problem. Okay, how to solve it now? First of all, obviously we want to use the induced EMF formula, that is BVL. Okay, so B is known, given, L is given, only V is not given. So we want to use this, but can we use this formula? We cannot use this formula because V is basically omega into L, but this omega into L is here. This V, value of V varies with the L. So whatever L is here, suppose I take a small distance x, then velocity here will be omega into x, and at the center velocity will be 0. So basically what we have to do, we have to take a integration of the entire thing. That is the main trick of this question. So epsilon, let us consider a small portion dl, or small portion dx rather. Okay, small portion dx at a distance x. Then what is the velocity here? Velocity here is omega x. So what is the induced EMF over here? Induced EMF will be B Vx into x. This is the induced EMF at this point, right? B is constant. Okay, B is constant obviously. B into x into Vx. Now what is Vx? Vx is omega into x into another x. This x is another free x. So what we got? We got B omega into x square. Now what is the total induced EMF? Total induced EMF, for that we have to start at this point, that is x equals to 0, and we have to come over here, that is x equals to L. So we have to integrate it from 0 to L, that is B omega x square dx. Because we are considering a small element, so dx will be there as well. Okay, dx will be here. Now we have to integrate it, so it will be sorry, I made a mistake. This will be dx, because we are considering due to the small element, right? So it will be dx. So it will be dx. So it will be only x, right? Now you will get B omega integral 0 to L x into dx. What is x into dx? X square by 2. So x square by 2, upper limit L, lower limit 0. So what will be the answer? So induced EMF will be B omega x square by 2, that is L square by 2. Okay, upper limit will be only there, so you will get half B omega L square. So this is the induced EMF. It does not depend on the number of turns of the spoke. So half B omega L square, option B is the correct answer. It does not depend on N. Okay, remember that. Next question. An aircraft with a wingspan of 40 meter flies with a speed of 1080 km per hour in the eastward direction at a constant altitude in the northern hemisphere, where the vertical component of the Earth's magnetic field is 1.75 into 10 to the power of minus 5 Tesla. Then the EMF developed between the tips of the wings. Obviously, EMF developed is B into V into L. But here, as usual, V you have to convert. So 1080 kilometer per hour, you have to convert it into meter per second. So what is the conversion factor? 5 by 18. So 18 into 6 is 108. 18 into 6 is 108, so it will be 60 over here, and 5 into 60 is 300. Okay, so 300 meter per second is the conversion. Now you have to put that value, just 1.75 into 10 to the power of minus 5, V is 300 and L is 40 meter. Okay, so now just what is 1.75 by the way? 1.75 is basically 7 by 4. If you know this conversion, it will also help. Okay, 3 into 4. So 10 to the power of minus 5, 1, 2, 3 zeros. So it will be 10 to the power of minus 2. Right? 3 zeros are here. So it will reduce the 10 to the power of minus 5. Now this 4 will cancel. You will get 3 7s are 21 into 10 to the power of minus 2. So it will be 0.21 volt. Okay, so 0.21 volt is the answer in this case. Next question. Two coils have a mutual inductance 0.005 Henry. The current changes in the first coil according to the equation I equals to Im sin omega t, where Im is 10 ampere and omega is 100 pi. The maximum value of induced EMF. Very interesting question. So what is the induced EMF? Induced EMF for mutual inductance is M di by dt. Same formula. Okay, only thing is that here current is not given like this. Current is given in a different form. Okay, so that form we have to use. Be it mutual inductance, be it self-inductance, formula is same. So basically what we have to do, you have to do the differentiation of this function Im sin omega t. Okay, now what is the Im is constant, it is coming out of the integration. What is the integration of sin 80? Differentiation of sin 80. Differentiation of sin 80 is A into cos 80, right? So omega cos omega t. Now what is the maximum value? When it is maximum, the cos theta can be equals to 1. This is the amplitude or the maximum value, right? For maximum value, we any cos function or sine function, we assume that they are 1. So the maximum induced EMF is M Im into omega. So M is 0.005. Im is 10 ampere and omega is 100 pi. Okay, so what is the meaning of that? 1, 2, 3. 1, 2, 3. So all of them are cancelled. So you get 5 pi. Okay, 0.005 means 5 divided by 1000, and those 3 zeros are getting cancelled with this 1000 over here. So it is 5 pi, not 50 pi. So 5 pi is the answer. Next question. A solenoid of inductance 2 Henry carries a current of I ampere. Magnetic energy stored in the solenoid is 1 joule. The value of I is. So what is the formula for magnetic energy? Magnetic energy is half Li square. Okay, half energy is 1 joules. Okay, L is 2 Henry and I is I square. So you cancel. So I square equals to 1 or I equals to 1 ampere. Okay, so correct answer is 1 ampere. Next question. If angular speed of the rotating armature of an AC generator is increased, the frequency of AC increases while the peak EMF remains the same. The peak EMF increases while the frequency of the AC remains the same. Both frequency of the AC and the maximum EMF increases. Both frequency of the AC and the maximum EMF remains the same. Now what is the maximum EMF? Maximum EMF generated in an AC generator is NAB omega. NAB omega. Now if you increase the, and what is the frequency by the way? Frequency is 2 pi omega. Okay, so if you increase the angular speed, that is if you increase omega, so you can see that EMF, maximum EMF is increasing, also the frequency is also increasing. So if you increase the angular speed, frequency and induced EMF both increases, so both the frequency of the AC and the maximum EMF increase. So correct answer is option C. Next question. The magnetic flux through a surface of area A placed in an uniform magnetic field B is defined as. So what we are trying to find? Magnetic flux. Magnetic flux is B dot A. Okay, so the dot product, magnetic flux is a scalar quantity, so it will be B dot A. Next question. To induce EMF in a coil, the magnetic flux linking must remain constant, must increase, must decrease, both B and C. So either it can increase or it can decrease. Okay, so both B and C. Next question. When a magnet is moved with its north pole towards a closed coil, the near end of the coil acts as north pole, south pole. No magnetic field is induced, both north pole and south pole are induced. So magnet is moved with its north pole towards a closed coil. Okay, it is moving towards a closed coil with north pole facing it. Okay, so the nearer end of the coil will act as another north pole so that it can fulfill the Lenz law. Next question. The magnetic flux linked with the coil varies as phi is equal to 2t square plus 2t. What is the magnitude induced at t is equal to 0.5 seconds? So what is d phi by dt? So magnetic flux induced is d phi by dt, that is 4t plus 2, and at 0.5 seconds. So you have to put, it's running faster. So 0.5 into 4 is 2, 2 plus 2, that is 4 volt. So I think the options are given in this question are wrong. The answer will be 4 volts. Next question. Which of the following is a consequence of conservation of energy? Lenz law is a conservation of energy. Next question. The energy stored in an inductor of inductance L in establishing the current I in it is half Li, Li square, Li, half Li square. So energy stored or the work done to establish a current is half Li square. So correct answer is half Li square. The following are the statements of self-inductance. The self-inductance of a coil depends on the geometry and on the permeability of the medium inside it. Self-inductance has proportional to mu, and it is also dependent on area, length, etc. So it depends on geometry. The self-inductance is a measure of electrical inertia and opposes the change in the current in the coil. So it is also a correct statement. So both statements are correct. Both statements are correct is the correct answer, not wrong. Both statements are correct. Option C is correct. But they are not assertion is a question. The direction of current induces in the loop ABC as shown in the figure. So you have to find the direction of the current induced in the loop ABC. Basically this will be 0 if current is not changing. So current has to change. So based on the current increasing or decreasing in this loop, the direction of current will also change. Now first let us understand what is the original direction of magnetic field. So original current is flowing in this direction, so our thumb aligned in this direction and our fingers curled towards the loop will give us the magnetic field at this point. So magnetic field will be into the page of the paper. So now if the current is increasing, then the induced current will be such that it opposes this magnetic field. So induced EMF will be such that it is out of the paper. Now if the magnetic field is decreasing, if the current is decreasing, then the induced EMF will try to strengthen it. Okay, so basically it's like a bank. Okay, if you are having extra money, you have to deposit it here. If you don't have extra money, if you are losing money, then it will try to support you by giving you extra money. Okay, now if current is increasing, the magnetic field will be out of the paper. Out of the paper means we will curl our fingers along the wire, and this will give you the direction. So if current is increasing, then the induced EMF will be ACB. It will be like this. So ACB. So it will be ACB. And if the current is basically if the current is decreasing, then it will be into the page of the paper. So it will be ABC. Okay, ABC. Now let's see what are all the options given in this question. Definitely if it is constant, there is no current, so this is wrong statement. Along ABC, if it is increasing, along ABC if it is increasing, but it is not, ABC it is decreasing. Along ACB if it is decreasing, if it is also wrong. Along ACB if it is increasing, along ABC if it is decreasing. So yes, if it is decreasing, current is decreasing, then it will be along ABC. So obviously option C is correct. Next question, the polarity of induced EMF in a coil is given by Lenz law. Polarity is given by Lenz law. Current in a coil changes from 1.6 ampere to 0.2 ampere in 2 seconds, inducing an EMF of 2.8 volt. The value of self-inductance of the coil is. So induced EMF equals to L di by dt. Okay, or equals to L. Di is 1.6 to 0.2. and time is 2 seconds. So it will be L into 1.4 divided by 2, that is 0.7 into L. Now induced EMF is 2.8 volt. So 2.8 equals to 0.7 L. So point cancel, and you will get 4 7s are 28. So L equals to 4 Henry. So L is 4 Henry. So correct answer is C. So with this we have reached the end of this lecture, and if you have any questions, any doubts, don't forget to mention that in the comment below. I'll be back with a new chapter very soon. Till then, bye.